All right, so today, now that we understand the simplicity of molecules and atoms, it's important to understand that life, albeit made of atoms and molecules, is really a series of events of chemical reactions that occur within the body, in particular, utilizing enzymes that we're going to see. So, to understand life truly, you need to look at it as just a whole bunch of chemical reactions. I know that takes the beauty out of life, but if you're going to look at it entirely scientifically, that's the way you need to really look at it. So any chemical reaction, whether it be in life or otherwise, occurs when the bonds between atoms are changed. So what I have here on the screen are six carbon dioxides and six waters. All right. What we have here on the right is a glucose molecule with six oxygen molecules, so O2, as it truly exists in nature. If you took the time to count all the red oxygens and all the white hydrogens and the black carbons, whether you're counting them in the left or right, you would find that they have the same exact number. So much like Legos, for instance, or any other toy, it's almost like you're separating the atoms and rejoining them into different forms. So that is, in its simplest way, that is a chemical reaction. And in any reaction, there are two things, or what are considered the reactants and the products. And albeit when you guys get to chemistry, you'll talk much more about chemical reactions. But this particular one, we're taking six carbon dioxide and six waters, and we're turning them into C6H12O6, which is glucose, and six oxygens. So in this, the reactants are the carbon dioxide and the water. Those are the materials that enter the reaction. And the products, in this case, are the glucose and the oxygen. Those are the materials that are created. But the truth is, albeit in certain cases very difficult to do so, any chemical reaction is technically reversible. So just as much as you took carbon dioxide and water to create glucose and oxygen, you could take glucose and oxygen to turn it back into carbon dioxide and water. In this case, the glucose and the oxygen are now the reactants, and the carbon dioxide and the water are now the products. So to explain more about chemical reactions, all reactions ultimately need energy to occur. They don't occur spontaneously. They need a certain amount of energy. Some will release energy, like in certain explosions or glow sticks, for instance, or classic sci-fi events. Some absorb energy, like for instance ice packs, but when all said and done, all reactions need some added energy. They don't just happen by mixing things and they spontaneously occur. Classic example would be like a match. All right, a match is a series of a bunch of chemicals that are just waiting to combust in the presence of oxygen, and they won't do so unless you provide enough friction or heat for that to occur. And once it does, it begins to combust. The reaction begins to happen. So that energy that is needed to be put into a reaction is called the activation energy. It makes sense. It activates the reaction. Some reactions require a lot, some require less. And ultimately, there's two types of reactions. Whether it be absorbing or releasing, there is still an amount of energy that needs to be put into it. So in the top graph there, even though the products have more ultimate energy than the reactants, they still need to overcome a certain amount of energy. Or in the energy releasing, same thing. The products might release more energy, contain within them less energy than the reactants, but again, you still need to overcome a certain amount of energy. Often heat is enough. Cooking, for instance, is basically you're adding heat to a bunch of chemicals, things like sugar and milk and water, you name it, and you're causing those chemicals to react ultimately to create something hopefully much more edible. But you're not just going to mix cake batter and then hope that it eventually turns into cake on its own. You need to add energy. And in a similar way, most chemical reactions will occur in the presence of heat, but sometimes heat isn't good enough. So in living things, we can only have so much heat. We're water-based. All right, if you put too much heat into a living thing, water starts to boil, and that's bad for most living things. So most living things rely on enzymes, which are proteins that ultimately lower the amount of activation energy so that the reaction can happen easier. And often they do it in a way that doesn't require the living thing to increase its temperature, because that could ultimately be bad for the living thing. So in this graph here, the blue line represents the amount of energy that would be needed without an enzyme, but the red represents what it would need just with the enzyme. Still needing energy, mind you, but the enzyme makes the amount of energy needed less and ultimately makes the reaction happen easier. Sometimes just by being present, the amount of heat that exists is enough to get the reaction going with the presence of that enzyme. Enzymes, side note, are often or always, as far as we're concerned, proteins. So a classic example when you digest lactose, which is a carbohydrate found in sugar, notice it ends in ose, and it breaks it down into two smaller monosaccharides, galactose and glucose. Your body can't digest lactose by itself for energy. It needs to digest lactose and glucose. So what your body does is it hopefully breaks down lactose into galactose and glucose so your body can digest those for energy. But again, lactose won't break down on its own. It needs energy, and in this case, it needs an enzyme to do so. So this is lactose broken down into these two molecules of galactose and glucose, smaller monosaccharides made from, in this case, a disaccharide, two monosaccharides linked together. And it does this in the presence of the enzyme lactase. Now, I know the words are starting to kind of conflict here, but lactase, or anything ending in ase, for that matter, tends to be enzymes. Almost always, you can assume that anything ending in ase is an enzyme, lactase being an example. So what lactase does is it is an enzyme that will grab ultimately onto lactose and split it physically into galactose and glucose. And in doing so, it requires the body to exert much less energy to make it happen. So some other concept you need to understand is that any material that binds to an enzyme is called a substrate. So lactose would be the substrate to lactase, the enzyme lactase. And it just doesn't bind to it anywhere. It binds to it on a specific spot on the enzyme called the active site. So here's a little cartoony version of it. So on the top here, we have lactase, the enzyme, binding to lactose, made of the yellow and the blue diamond there. And it fits perfectly into a portion of it called the active site. And when it binds to it, the enzyme, ultimately what it often does is it twists or bends, and it physically separates the molecule, breaks them down. In this case, separating glucose from galactose. Now, the important thing is there, as they're showing on the bottom there, is that it is specific. All right, yeah. So lactase doesn't just break down anything. All right, that would actually be quite detrimental to the body if it just started grabbing onto things and separating them. So a similar disaccharide like sucrose, which is table sugar, may almost fit into the enzyme, but it doesn't completely fit. And because it doesn't completely fit, it will not be broken down. There's another enzyme out there somewhere whose job is to break down sucrose, and perhaps you can guess what the name of that enzyme is. So some things to keep in mind is that the enzymes are not changed. So when lactase is done breaking down a lactose, it can be used again and again and again and again. As I mentioned before, they only bind to specific substrates. So as we were just discussing, the lactase will not break down sucrose, nor will it break down any other molecule. It's specifically designed to break down lactose, and that's it. Now, some things can affect how well enzymes work, and two primary factors include pH. The pH of the cell, for instance, could be too high or too low. And because of that, the enzyme may not work as well. And the temperature can be too high or too low. So it could be too warm, too cold. This is particularly why it's important that you get, if you ever have a fever, for instance, or you are ever out in the cold, they may take your temperature, because if your temperature is too high or too low, there are enzymes in your body which may not function as well. So this is why it's particularly important that your body regulates its temperature and its pH, in part to allow the enzymes in your body to do what they do to do it well at that very healthy range of pH and temperature.